So we've got trig equations part 2. Let's go ahead and get our reference sheet down. We've got our two main triangles. Small angles pi over 6, other one's pi over 3. We've got our plus and minus sign diagram. All seniors take calculus. The other things I'm going to add in are these degenerate triangles. So that way we'll talk about these today. So we've got 0, 1, and 1. So this is a 0-degree angle or a 0 radian angle. And then likewise, we have vertical angles. So if the angle were straight up, what would that triangle look like? So that angle should be pi over 2. Of course, we can't draw it exactly. Now this horizontal side should be really skinny, really tiny, 0, and then 1 and 1. Other things we've got our trig identities. So write down any of those that you think you'll want, or get in the habit of at least writing those out. And the more you write them out, the less you'll have to write them out in the future, because then you'll only need to write one, and then you'll remember the other ones. Actually, don't even want to write any more of those, any of the Pythagorean identities. We're not going to use those much today. It will be handy for the IC, some of these Pythagorean identities. We have cofunction identities. Let's go ahead and write one or two of those down. And then, of course, I remember that these two can switch. I can have cosine of pi over 2 minus x is sine. Likewise here, those two can switch as well. Then we also have the even odd identities. So write those down if you need to, or keep them handy. The examples we're going to see aren't going to use those today, but they could come up in these types of problems. So keep those handy if you don't know them. And then the other thing I want to write down is our steps. So let's just keep this first page as our reference sheet for solving these types of problems. We've got our trig information, and now let's rewrite the steps we were coming up with on Friday. The first step we were doing was determine the reference angles, and the quadrants. And then we want to figure the initial solutions. And then once we have the initial solutions, we can include the periodicity. This is like the key part of these problems. This is the key in terms of understanding trig, really, is done in these steps. And as I was mentioning on Friday, this is only part 2 of solving these problems. There's actually going to be 3 parts, and we introduce a little bit of what can happen next after this. Our part 3 is going to be to solve for specific variables, solve for a specific variable and or values. And so our example that we started with, or I guess ended with on Friday, we took our sine function, we solved the sine equation, and now we were asking, what happens if I want to solve something like sine of 3x equal to negative 1/2? So instead of just having an x, we have a 3x in there. But all that's going to do is change some of the steps we have to do at the end. We're going to have a little bit more work to do once we've done all of these part 2 steps. So what I like to do whenever you have an equation like this and we want to solve it, if the argument inside of the trig function isn't just a variable, if there's a 3x, it could even be like a 3x plus 2 or something like that, then we can always make a substitution. We can call that theta. And now we've just reduced the problem back to the first problem we did on Friday. And so we're going to work with those part 2 steps. Determine the reference angles and the quadrants are the first 2 steps, probably the most important with these as well. So what is our reference angle here? And keep in mind when I say reference angle, I now mean the reference angle for theta. We'll deal with solving for x in that last step after we first do these part 2 steps. So to find our reference angle, again, you're going to pull up your triangles. And we are going to look at the ratio and the trig function. So the plus or minus doesn't matter yet. That's going to happen in part 2 or the second step with the quadrants. We are just looking for a ratio of 1/2. So it's going to give me those 2 sides, 1 divided by 2. And which angle has a sine ratio of 1/2? It's going to be this pi over 6 here. So sine of pi over 6 gives me that ratio of 1/2. That's going to be our reference angle. And then the quadrants we want, we pull up our plus minus sheet. And since we want a negative value for sine, where is sine negative? Positive in the first quadrant, positive in the second quadrant, which means in the third and fourth quadrants, sine is negative. Only tangent is positive in the third quadrant. Only cosine is positive in the fourth quadrant. So sine, negative in those 2, quadrants 3 and 4. First 2 steps, those are the key things. And then, of course, to really get your points, I guess, you would want to get this third step in finding the initial solutions. And how do we find our initial solutions? I suggest drawing. I always like to draw these out in the coordinate plane. So we need a reference angle of pi over 6 in quadrants 3 and 4. So in quadrant 3, it'll be down here like this. With that angle there is pi over 6. And in quadrant 4, it'll be down here like this. Where that angle here is pi over 6. And now how do we find our specific solutions? Just got to remember how to count. So you can always write this on your cheat sheet if you want. I always like to, if you want to keep it handy on the problem you're working in, that's usually what I do. So that way I don't have to write out all of them. Since we know the reference angle is pi over 6, let's write down our counting tools. So let's just write down the ones for a 6 in the denominator. So we've got pi and 2 pi. And so how do we find the exact angles corresponding to these reference angles? We got to start from the positive x-axis. And then if I go halfway around the circle, 6 pi over 6, plus 1 more, we'll get 7 pi over 6. So that's one of the answers for theta. The other answer, I need the reference angle for this guy. So I can go 2 pi all the way around the circle and then back 1. So 12 pi over 6 minus 1 gives us 11 pi over 6. And then our last step for part 2 was just to add on the periodicity, plus 2 pi k. But now we got a little bit more to do. So now our solution was, or excuse me, our real variable is x. That's our specific variable we want to solve for. And really the equations we have are 3x is 7 pi over 6 plus 2 pi k, and 3x equals 11 pi over 6 plus 2 pi k. So how do we solve for x? Just basic algebra. We want to divide both sides by 3. And just remember to divide both of the terms. So when I divide 7 pi over 6 divided by 3, we get 7 pi over 18. Plus, you can write it as 2 pi k over 3 if you want. Or, so let's go ahead and divide both these sides by 3. So we'll have 11 pi over 18 plus, you can write it as 2 pi over 3 times k, if you want to keep the k outside of the fraction. It's all multiplication, so it's all the same. So if that's all the problem said, to find the general solution, to find all the solutions, that's all we would need. This would be our answers. We also maybe want to specify our k values somewhere. On Friday, we were writing k is this guy. We usually just list out a few terms and include some dots, indicating that it can go up or down in either direction by integer steps. The other thing we commonly write, if you don't want to write out all this, is this. So this sideways E means an element. So we introduced this way back a little bit when we were talking about set notation. This just means K is an element of the set of integers. The Z, it's called a blackboard Z. It's like a Z with an extra line going across the middle. Z stands for some German word. Whatever the German word for integers or something like that is the reason we use a Z for integers. So plus and minus counting numbers. So a little bit of shorthand if you just want to write that on homeworks and whatever, what have you. So I do want to talk about, well, sometimes the problem is stated a little bit differently. Sometimes we're essentially given the same thing, but maybe it asks for specific set of values, not just the general set of solutions. So find x in, let's say, minus pi to pi. Satisfying sine of 3x equals negative a half. So same equation, we've already solved this, but now this isn't it's not answering the question that's asked. It's not wrong. It's just not as specific as the solution wants in this problem. So if it gives you a solution like this, or finding values between minus pi and pi, I like to solve these problems the exact way we did already. Find the general solutions, and then once we find the general solutions, we can find the specifics based on the range they specify. So that's kind of what I mean by this third part here. Find the specific variable if we need to isolate that x, and then also any specific values given a range that they might have specified in the problem. So let's go through that. I want to make a table with this, so I think it's a nice way to organize the information and understanding how these linear sequences work. So let's go ahead and write down our solution, or at least our information, x in minus pi to pi. And the solution we found, solving sine of 3x is minus 1/2 x, or excuse, minus 1/2, is x equals 7 pi over 18 plus 2 pi over 3k, and then x equals 11 pi over 18 plus 2 pi over 3k. So what I'm going to do when we want to find specific solutions, First thing I'm going to do is change the denominators, because what we were going to do is pick different values of k and then add these numbers together. We want specific angles. This is a general set of angles, since k can range from all sorts of different numbers. And since we're going to be adding those, it helps to put the denominators the same. 7 pi over 18. 2 pi over 3, I got to multiply by 6 over 6. So 12 pi over 18 times k. 12 pi over 18. Okay. And this should happen since the period factors are the same. They should have the same steps, as we will see. So our step is actually going to be a step of 12 with a common fraction of pi over 18. And so let's make a table. Let's do 7 pi over 18 plus 12 pi over 18 times k, and 11 pi over 18 plus 12 pi over 18 times k. And the column headings are just going to be different values of k. So our rows are our sequences, our general solutions, and our columns are different values of k. Now, because our solution set includes negative values, negative pi all the way up to pi. So I'm going to put k equals 0 somewhere in the middle, because we're also going to want negative values of k. So I'll just put 0, 1, 2, negative 1, negative 2, negative 3. And we're not going to need to do all of them. I always recommend starting at 0. It's always the easiest. So these are the values of k at the top. You just want to plug in these values of k into the sequence and compute it in the table. So plug in 0 for k. It'll kill this term, and we just get our initial solution we found, 7 pi over 18. Likewise, for this sequence, when I plug in 0, we'll get 11 pi over 18. And now what do we need to do? Let's check this next one. What happens if k is 1? When I plug in 1 for k, I'll have 12 pi over 18 plus 7 pi over 18. So 12 plus 7 gives me 19 pi over 18. And then here, with k is 1, we'll have 12 plus 11 gives us 23 pi over 18. And now let's check back. So some more little notes you can add to yourself in these problem solving processes. If we want x within a specific bound, the denominator we found, 18, and we need to find solutions between minus pi and pi. So pi is 18 pi over 18. So that's going to be our upper bound. Our lower bound then is going to be negative 18 pi over 18. So I'll just make a little note, stop when we're outside of that, when we're bigger than this in absolute value. And what do we have? Here's 19, here's 23. So these are both bigger than pi. So we actually don't need those solutions. So we can cross those out if we want. And since we're already bigger, we don't have to keep going. We don't have to find anymore. So what we want to do now is check some of these other values and keep going backwards until we hit a stopping mark. So we've got 7 pi over 18. Now if k is minus 1, I'll have negative 12 pi over 18 plus 7, or 7 minus 12 will give me negative 5 pi over 18. Same thing here. K is negative 1. We'll have 11 minus 12 gives me negative 1 pi over 18. And those are still good. They're still within a range, so we're going to keep going. So now we have K is negative 2. So negative 2 times 12 is negative 24, plus 7 is negative 17 pi over 18. And likewise here, 11 and negative 24 is negative 23. Excuse me, negative 13 pi over 18. Now, there's also an easier way to do this. Instead of plugging in the 2 and then multiplying and adding, our next one would be to plug in the 3, multiply and add. You can actually do it a little bit easier. So these are what's known as linear sequences. It's essentially a linear function. And if you notice, what's special about a linear function, it has the same slope. So same constant change in y for the change in x. Essentially the same thing going on here. How do we go from 7 to negative 5? I subtracted 12 pi over 18. What if I go from negative 5 to negative 17? We subtract 12 pi over 18. So how do I get this next one? I can just take the value I'm starting out with negative 2, subtract 12 in the numerator. So our next one would be negative 29 pi over 18. Same thing here. I'm at negative 13, subtract 12. So we'd be at negative 25 pi over 18. So this is like you can think of this as like the slope. I am subtracting 12 every time we move to the left, subtracting 12 pi over 18 specifically, adding 12 pi over 18 every step we go to the right. And what do we notice? So here, my numerator is bigger than 18 for both of those. So we actually don't need those solutions either. So since our stopping bounds were 18 over 18, we only want these 6 values. So that is our specific solution. Since we're specified a range, we only have 6 answers. So a couple tips. When the argument is like 3x, and if they give you a range, a normal period is 2 pi for sine and cosine. So if they give us a range of 2 pi, and the argument is a 3x, then there's always going to be twice as many solutions as the multiplying factor. So that 3x, sine of 3x equals negative 1/2, we should expect 6 solutions within a given period of 2 pi. If it were sine of 4x, we would have 8 solutions. 5x, 10 solutions, as long as that range is a distance of 2 pi. So sometimes you'll see 0 to 2 pi is where they want to look for solutions, is going to be the most common if they specify a range. But you'll see this as well. Sometimes we say minus pi to pi for a solution set. So the other thing that might come up is on WebAssign. I'm going to keep my solution as this. That's a good enough solution for me. Of course, if it was on a written homework and you turned in something like that, that's fine for me to grade. I don't know if Ali would want you to write it any differently, since it's pretty clear what your solutions are. If on WebAssign, I think oftentimes they want you to put them in order, and sometimes they'll say find the smallest solution, then the next smallest solution. So sometimes you just might have to type them in the correct order. So the smallest solution would be this guy, negative 17. Then the next solution increasing would be this guy, negative 13 pi over 18. Then just keep increasing until you get to the biggest value. So something else that might come up. Any questions on that? So there was a bit of work in that step, in that third step, especially if we have to find a specific solution. It's not too difficult though. It's mostly just adding fractions and then minding your bounds. So I went through that pretty slowly, just re-practice adding these fractions. And after you do a few, you'll be able to do those a lot quicker. Let's talk about what can happen in the beginning of the problem. So that's kind of like the end of the problem. If we wanted to make things a little more complicated, we've got a 3x instead of just an x. How can things get a little more complicated at the beginning of the problem if we need to do some sort of work before isolating our trig functions? So that's going to be our primary first step, is to isolate the trig functions. And we usually do this by factoring in trig identities. And as well as just general algebra. So these problems can get a bit long. And the next one we're going to do, it's going to take us probably the rest of the class. Because even though there's only one step in part one, the process of doing all of the algebra can be a little lengthy. Then we got to do this part two stuff with the reference angles and finding the specific solutions. And then part three, we got to be careful if there's any sort of periodicity, weird periods of, we're solving for a 3x or something to that effect. So let's see what one of these problems can look like. We'll have sine of 2x times cotangent squared of pi over 2 minus x is equal to sine of 2x. And I'm just going to solve for the general solution, not give a specific solution again here, since I don't think we'll have time to do a lot of that extra arithmetic at the very end. We're also going to have like 3 different trig equations to solve, and we'll see how these come out. So what do we want to do? We want to isolate our trig functions and set them equal to constants. Once we're there, that's when we're on part 2. If we look at the last problem, it started off with sine of something equals a constant. And so if we can get the problem to a system of equations or a set of equations that are like this, I can then move on to this part 2 trig problem solving. So how do we do that? Factoring is going to be a huge thing that comes up a lot, because a product of factors that is equal to 0, I can set each term equal to 0. And so that gives us another hint that we also like having these trig equations set equal to 0. So be careful with something like this. You don't want to divide the sign on both sides. If you do that, you'll miss half of the solutions. What we want to do is add and subtract. Put everything on one side of the equation. And now we have a function, a trig expression equal to 0. Sorry, and that's a sine of 2x. And now how do we solve this? We want to factor this sine of 2x out. Now it's looking a little better. We've got a product of two things equal to 0. However, this argument's a little messy. This one, well, kind of messy. It's a 2x, but we can't really do anything about it. This one's, we don't really like addition subtraction in there. We could solve it the same way, but this is also a cofunction identity, namely cotangent of pi over 2 minus x is tangent. So let's go ahead and take advantage of that identity to simplify things a little bit. And remember, cotangent squared of something really means compute the cotangent. This should say cotangent of pi over 2 minus x, then square it. So cotangent of pi over 2x, pi over 2 minus x is tangent of x, then square it. So we're a little bit closer. Now we have a product of two terms that have been simplified. I can take each term in the product and set it equal to 0. And we're getting closer. This term's good. We're ready for part 2 on this expression. We just got to find our reference angles and continue from there. Let's get this equation there. Most students, when you want to solve this, will do this. You'll add the 1 over. And then what do we need to do? If we take a square root, what do we got to remember? The plus or minus. Always remember this plus or minus if you see tangent squareds, cosine squareds, and we've seen a lot of these trig function squareds, right? They come up in our identities. So remember the plus or minus if you solve it this way. So really what we're going to have is tangent of x equal to plus or minus 1, which I'm actually going to write out as two equations, is what we mean by that. Tangent of x equals 1, and tangent of x can equal minus 1. So the other way we could solve this, of course, is if we come back and if we could factor this as a difference of squares. Tangent x minus 1 times the quantity, tangent x plus 1, and we would get both of those equations. So careful with all that stuff. Remember, we didn't cancel the sign in the beginning, so we would get this solution. And careful with the plus or minus here. If you miss either of those steps, you'll miss one of these equations in a large set of the solutions. Okay, so now we're ready for part 2. We've got our trig functions isolated and set them equal to a constant. So what is part 2? What's our first 2 steps? Reference angles and quadrants. So let's go ahead and work with this first guy here. Whenever sine and cosine are equal to 0 or 1, it's going to be one of these degenerate triangles. So pull up our reference sheet. Which triangle has sine equal to 0? Because the only triangles with zeros appearing in their side lengths are these degenerate ones. So this angle here, if we see sine of that, is going to be 0 over 1. So sine of 0 is 0. So one of our solutions is 0. And the other solution is pi. So remember, we could flip this degenerate triangle, and if it was a pi angle, the second hand should be smashed on the axes, both with a distance of 1. We consider the x side length as -1, hypotenuse always +1, but the vertical side would be smashed together, so 0. And we see that sine of that would be 0 divided by 1. So our other solution is pi. So for those ones, parts 1 and 2 are reference angles and quadrants are essentially dictated just by finding those degenerate triangles, primarily because They're quadrantal angles. They're not entirely in a quadrant. So let's go ahead and solve this out. We have, a 2x equals 0, and a 2x equals pi. And I forgot, let's go ahead and add in the periodicity. So 2 pi k for each of those solutions. And since we were considering it just sine of theta, we have plus 2 pi k with each of the thetas. And then now, when I solve for x, let me get a light there, getting a little dark out. When we solve for x, 0 divided by 2 is 0. And now we'll have 2 pi divided by 2 times k. So just pi times k. And then this guy here, pi divided by 2, just gives us pi over 2. And then again, the 2 pi k divided by 2 will just give us pi k. That's that guy. And now we've got these two equations as well. So we're in part 2 again for these guys. Well, I guess we just did part 2 and 3 since we plugged in the 2x, but our part 3 wasn't too lengthy there since we just want the general solution. Here we're back in part 2. What is our reference angle? It's the first thing we want to find. Go to our sheet. Which triangle has a tangent ratio of 1? It's going to be this guy here. Tangent of pi over 4 gives me 1. And since these two values are the same value up to a plus or minus sign, right? So they're going to have the same reference angle because the ratio is still 1 up to a minus sign. The quadrants are going to be a little bit different, though. So where is tangent positive? First and third quadrant. Whereas this guy is going to be positive, or excuse me, tangent is going to be negative in the other two quadrants, so 2 and 4. So what are the initial angles we want to look for? We are looking for a reference angle of pi over 4 in quadrants 1, 2, 3, and 4. So we want a pi over 4 reference angle in every single quadrant. Let's go ahead and find all those. First one, pretty easy, just pi over 4. And then in quadrant 3, if this reference angle is pi over 4, what is the actual angle measure? We go 4 pi over 4 plus 1 more. So 5 pi over 4. That's where tangent is positive, quadrants 1 and 3. And then in quadrants 2 and 4, we have an angle of pi over 4 there. And how do we count that? 4 pi over 4, and then back 1 gives us 3 pi over 4. And then in the fourth quadrant, how do we count that guy? We go all the way around, 8 pi over 4 minus 1 gives us 7 pi over 4. Those are our specific solutions, our initial solutions. we need to add in our periodicity. So tangent and cotangent are the odd men out. They have a different period than sine and cosine. So sine, cosine, as well as the reciprocals of those, cosecant and secant, have a period of 2 pi. So you're always going to add a 2 pi k once you find your initial solutions. That's only going to change if there's like a 2x or a 3x there. For tangent and cotangent, there's no scaling factor in front of the x. So all we have to do is add on pi k. And this is because the period of tangent and cotangent is pi. Tangent's kind of just the magical one that's every other quadrant you start to have the same values. So we only need to add pi k's for tangents. And with tangents, you often end up doing a little bit more work than you need to. So I actually didn't write the pi k's on these ones. And why not? In general, when we did the correct problem solving method, we found a solution in quadrant 1 and 3, solution in quadrant 2 and 4 for the negative value. We had our pi k, but I claim we actually don't need to write these two solutions. They're not wrong. They are correct values that will satisfy the equation. However, this pi k, this k stands for some integer. We can write that somewhere if we want. K is in z. And just as we did with the last problem, if I had specific ranges that we wanted to find, we could plug in specific values of k. When we write it like this, we just consider all values of k valid, meaning I can plug in any of those, and that we're already counting that in this statement. So what's going to happen if k is 1? I would have pi over 4 plus pi, which is 4 pi over 4. So we've got pi over 4 plus 4 pi over 4 gives me 5 pi over 4. Likewise, over here, what's going to happen? 3 pi over 4 plus 4 pi over 4 gives us 7 pi over 4. So again, when k was 1. So it's not that these are wrong. It's just that we are actually already counting them in these sequences. So what's going on geometrically here? This solution, what does it mean? It means start at pi over 4 and then add on any multiple of pi. So halfway around the circle. So this solution here includes this angle plus halfway around the circle, plus halfway around the circle, plus halfway around the circle. So it's going to hit every angle in the first and third quadrant with a pi over 4 reference angle. And no matter how many times we wrap around. So any of the coterminal angles with these two, this sequence will hit them. Likewise over here, we start at 3 pi over 4 plus pi plus another pi plus another pi. We're always going to hit one of these two reference angles. And with all of the values of k, we will hit all of the coterminal angles. So it includes the entire solution set in that statement. So the last thing I do want to say is that these are some weird things that'll happen with the algebra of sequences. And as you guys work with these a little bit more, you'll understand them a little bit more and get a little more comfortable with them. I do recommend practicing these, especially if you have to take up the Calc 2. Calc 2, you'll do a lot more with sequences. These two sequences here, we can actually combine and write it as one single sequence. So I'll leave that as a homework for you guys to think about how to do. I think it comes up on WebAssign, where with sine and cosine, you almost always have two separate solution sets with two different seeding values, and then of course your periodicity factor. But in certain cases, like the degenerate triangles, we could actually combine these and write it as one sequence. And I think you guys will have a few exercises on that to practice and work with. Any questions?